Okay, great. So I'll hand over to you now and you can get going. All right, thank you so much.
Thank you. Yeah. Okay. Thank you everyone for attending this session. And yeah, my name is Yuezhi Mao. I'm an assistant professor at San Diego State University, and I used to be a grad student in Professor Martin Hadgarden's group, so where I worked on the development of energy decomposition analysis methods. So yeah, today I'm going to give you some introduction about the features available in Q-Chem. So as many of you might know, energy decomposition analysis is like a quantum chemistry methods or a family of methods which can be used to study non-covalent interactions. So non-covalent interactions are so important in modern chemistry in many different areas, such as design of ligands for organometallic catalysis or enzyme catalysis or drug protein binding, and also supramolecular chemistry, all these different areas. So yeah, we definitely want to use theoretical and computational chemistry tools to investigate and interpret these interactions. So one a typical approach to calculate the interaction between molecules is using this so-called supramolecular approach. So you can just you pick your favorite quantum chemistry method and then calculate the energy difference between the intermolecular complex and also the sum of the fragment energies for each molecule in your complex, and then this give you a one number, which is total interaction energy, but this one number doesn't have a lot of physical information about this a specific interaction. So energy decomposition analysis is designed to further partition this total interaction energy into a couple of physically meaningful and also chemically intuitive components, including permanent electrostatics, Pauli repulsion, dispersion, polarization, and charge transfer. So this is decomposition offered by the current ALMO-based energy decomposition in Q-Chem, but there are other ways to partition this total interaction energy. So these EDA methods are particularly useful for a couple of things. For example, it can be used to understand specific interactions, such as hydrogen and halogen bonds, or some other different interactions like pi stacking, ion pi interactions, and so forth. And also you can use this method, combine this method with, for example, chemical reaction study tools. So you can investigate the role of non-covalent interactions in chemical processes. And the EDA method can also be used to guide the development of other theoretical models, such as molecular mechanical force fields and also machine learning potentials. All right. So I want to give a brief overview of the EDA methods available in Q-Chem. So there are two major family of methods, I would say. So the first big family of methods is ALMO-EDA, developed by the Hadgarden group at Berkeley. So there are so this method has been made available for many different scenarios. For example, a DFT-based calculations for non-covalent interactions, and the adiabatic EDA, which is a method to decompose molecular properties like a structural change and vibrational frequency shift due to intermolecular interactions. And there are also EDA methods developed for bonded interactions and interactions calculated using correlated methods such as MP2, and also interactions involving electronic excited states. And another family of method I should mention is SAPT CDFT EDA, developed by the John Herbert group at Ohio State. And so this method works slightly differently. It uses SAPT, which is a method which can give you both the total interaction and energy and the decomposition. So it doesn't go through the supramolecular approach. And then the constrained DFT method, CDFT, is used to separate the charge transfer from the SAPT induction. But today I will only focus on two things. One is the most recent version of the ALMO-EDA method for like a DFT-based calculations of non-covalent interactions. And I will also talk about the adiabatic EDA method. So the EDA method based on absolutely localized molecular orbitals, the ALMO-EDA decompose the total interaction energy, which is energy difference between the final state, which is a full complex, and also then between the final state and the initial state, which is just a few isolated fragments. And this decomposition is achieved by inserting two intermediate states where these fragments are only like partially interacting with each other. So the first intermediate state is called the frozen state. So in this state, we move the like isolated molecules to the position as they are in the complex, but we keep their the fragments on electronic structure unchanged. So this energy change, the energy change associated with this step is called the frozen interaction energy. And this is going too fast. And the second intermediate state is called the polarized state. So in this state, we allow the electronic structure of each fragment to relax in the presence of other fragments, but we don't allow the inter-fragment orbital mixings. And this is enforced using the ALMO scheme. And this energy change is defined as the polarization energy. And finally, we remove other constraints and just so charge flow between different fragments will be enabled. And this final energy lowering is defined as the charge transfer energy. Okay, so so using these three terms defines like the first generation of the ALMO-EDA method. And also I should mention that besides these three terms, there if you are decomposing the total binding energy rather than the interaction energy, the binding energy is energy difference between the full complex, energy difference between the full complex and the fully relaxed monomers. Then there is another term, which is a geometry distortion, which accounts for the energy penalty of change the geometry of each monomer from their own like relaxed structure to their slightly distorted structure in the complex. Okay, but yeah, so like this method has received quite a lot of new developments in the last couple of years, and now we have the second generation ALMO-EDA method, and now you can see we decompose the total interaction energy into 5 terms. So just want to list a few like new advances. So first, we enable the further decomposition of the frozen interaction into 3 terms, which are permanent electrostatics, polyrepulsion, and dispersion. And we also like introduced this like a new approach that's based on fragment electric response functions to which can have a different way or more like to separate the polarization and the charge transfer term. And in this new decomposition, there will be, it will have a well-behaved basis limit, since otherwise when you have a large basis set, then the boundary between the polarization and the charge transfer becomes ambiguous. And the third one is actually a very recent development from the Hart-Gordon group. So this is so this enables like a further decomposition of the polarization and the charge transfer. So the polarization will be partitioned into each fragment's own contribution, and the charge transfer can be decomposed into like this pairwise like a donor-acceptor interactions. And this decomposition is done using a non-perturbative approach, so different from the original charge transfer analysis in Q-Chem. And also it offers like very useful visualization tools. Like you can see like the orbitals involved in the polarization and the charge transfer interactions. Okay, and another unique feature of the second generation ALMO-EDA is it can incorporate solvation effects throughout the entire procedure with like implicit solvent models. And this scheme looks quite similar to the original like a gas phase ALMO-EDA scheme, except that now we are decomposing the energy difference between the complex solvated and also the individually solvated monomers. So now like each of these energy components are calculated with a solvation effect taken into account. And in this scheme, when using this scheme, you can find that the primary effect of this like a continuum solvent model is usually it like damps the electrostatic interaction. So now just want to show you a few applications of this ALMO-EDA method so you get an idea what it can do. So first, it can be used to identify the fingerprints of different non-covalent interactions. So this is a example in the like first like ALMO-EDA 2 paper. It's showing the decomposition of the interaction in the hydrogen bonded and the pi stacked adenine thymine complex. And from this decomposition, you can see for the hydrogen bonded structure, the interaction is dominated by permanent electrostatics. And in the stacked configuration, it's the most significant contribution is dispersion, but also there is a significant favorable contribution from electrostatics as well. And this is a more recent example. Like we used the solvated version of ALMO-EDA 2 to investigate how these different substituent groups on these phenyl rings can change the binding of this activated CO2 at the catalytic site of this transition metal complex. And we find that while both of these substituent groups are positively charged, they change they modulate the CO2 binding through completely different mechanisms. This one is through the reduction of the polyrepulsion, while this one is from the large like stabilization from permanent electrostatics. And ALMO-EDA 2 can also be used to assist the development assessment of force fields. So this was from like a pretty early paper of mine. So it's we compared the terms in ALMO-EDA and also the terms in the like amoeba, which is a polarizable force field. And we find that also like amoeba gives quite like a decent overall interaction energies for these like water-water or ion-water interactions. We find that like the agreement at the level of each energy component is quite full. For example, you can see there's a large gap between the permanent electrostatics given by amoeba and that given by ALMO-EDA. And most recently, the Teresa Hart-Gordon group at Berkeley had developed a new like a polarizable molecular mechanical model called MB-UCB, and this method, the development of this new model used ALMO-EDA data for training and also testing. So you can see now, like in this new model, it achieves the component-wise agreement with the ALMO-EDA results. So it's different from the original amoeba model, where the accuracy more or less depends on the error cancellation between different terms. I also want to quickly go through the adiabatic EDA method. So the EDA method we just talked about is referred to as a vertical EDA, where it's because it's just performed at a single structure. Usually it's a optimized structure of the intermolecular complex, but you can do it differently, can relax the complex geometry on each of the intermediate state, like each of the the frozen, polarized, and the fully relaxed potential energy surface. And then the energy terms can be defined as the difference between these stationary points on different potential and on these neighboring potential energy surfaces. But more importantly, this is a useful method which can partition not only energy but also molecular property shifts into contributions from frozen, polarization, and the charge transfer. So here is a example of this the application of this adiabatic EDA, which is just a water chloride complex. And you can see that this a near linear hydrogen bond structure, as well as this significant red shift in the OH stretch frequency due to charge transfer, because only when charge transfer is engaged, this a large change will take place. Okay, and let me see the time. Yeah, so probably I can go through this very fast because I would like to give you some time to do the practice. And so I would like to mention that so to make it easier to use, we offer some option sets in Q-Chem for these EDA methods. So for EDA 2 = 1, it does the frozen decomposition, and I'll use the FIRF for polarization. And when it's set to 2, it will use the original ALMO polarization, but frozen decomposition is still performed. So some general recommendation is, this EDA 2 method should always be used with a dispersion corrected DFT method. Otherwise, the dispersion term is just not meaningful. And in terms of the choice between these two options, I think from my own opinion, the option 1 should be used for a small to medium systems where a large basis set calculation is affordable. While if your system contains hundreds of atoms and a large basis calculation becomes too expensive, then you can go back to a double zeta basis set. And in that case, you should choose the EDA Q = 2 option set, because with a small base set, the FIRF method doesn't really help. Okay, it's not really necessary, I should say that. And also here, I would like to mention that, so you just need to turn on this solvent method in the RAM section of Q-Chem, so then the Solvation model will be incorporated in the EDA 2 calculation. Professor John Herbert will have another lecture introducing the solvent method later today, I think. And then EDA 2 also has a lot of visualization tools you can use when running this method. And for details, you can refer to the Q-Chem menu. So this is the input, and for a decomposition of the water sodium interaction with a SMD solvent water. Okay, and so in the output, so here are the basic 3 terms: frozen, polarization, and the charge transfer with the Solvation incorporated. Okay, And here it shows some frozen energy decomposition. And the numbers you should look for are the classical electrostatics and the Pauli repulsion with the solvation incorporated, and also a dispersion term. Currently in the ALMO-EDA soft method, the dispersion interaction is not really like affected by the solvation. And yeah, you may find like this output probably give you a little bit too much information. So I do plan to like even further simplify the output format for the next release. And yes, then about adiabatic EDA. So you need to use these two RAM variables to do the force calculation on the frozen and the polarized surface. Here is a quick example. So this is a practice for the ALMO-EDA 2 method. So it's a water chloride complex, and so we are going to use the EDA option 2 because we are using a relatively small basis here. But now, we are going to use add the BSSE correction for the same reason. And you will be comparing the EDA results in vacuum and in a solvation environment. So I think you will see some difference in the you will see the solvation will make a difference to the interaction energies and their components. Okay, I think I can stop my presentation now and leave a few minutes for the practice.